In this two-part video series, we'll explore two non-parametric classification tools, KNN and trees. Consider an example. Researchers use high-resolution aerial photography to monitor changes in land cover over time. Though a human might be able to identify land cover in a photograph, it isn't efficient when we have a lot of land to cover. With this in mind, we can build a machine learning algorithm. Suppose we want to be able to distinguish between three types of land use, asphalt, grass, or trees, using two predictors, the land's greenness and vegetation index as captured by a photograph. Data for 277 images are shown here. As a theme in machine learning, to classify land use, we might first reach for a parametric algorithm. These algorithms make very specific assumptions about the relationships of interest. In general, when these assumptions make sense, parametric algorithms are great and very powerful. But when these assumptions don't make sense, we should use something else. In this video series, we'll consider two non-parametric classification alternatives, k-nearest neighbors and classification trees. Let's start with KNN. In fact, the idea here is very similar to using KNN in regression settings. As an example, let the black dot represent greenness and vegetation for a new image. Suppose I asked you to classify this image using information from only the k=1 nearest neighbor. What would your classification be? Well, the one neighbor in this small neighborhood is a grass image, so it makes sense to guess that our new image is also of grass. But from KNN in the regression setting, we also know that by only looking at the one nearest neighbor, our model might be sensitive to local noise and might be overfit. So suppose I asked you to classify the image using information from the k=3 nearest neighbors. Well, among the three nearest neighbors, one is grass, the red dot, and two are trees, the gray dots. Since the majority here are trees, it makes sense to guess that our new image is also of trees. Finally, suppose I asked you to classify our image using information from all k=277 nearest neighbors in our dataset. In this entire dataset, there are 59 asphalt images, 112 grass, and 106 trees. Since grass is the most common category, we'd then guess that our image is also of grass. And this would likely be a bad classification, since our new image is pretty squarely situated among images of trees. Mainly by considering such a large neighborhood size K, we're going to end up with an overly simple model that loses the local trends. The KNN algorithm for building a classification model of some categorical response variable y by predictors x is summarized here. For a given value of the tuning parameter k, we take the following steps to classify or predict the y outcome of a new data point. First, we identify the k-nearest neighbors of the data point with respect to its x values. And by default, nearness or distances are measured with respect to Euclidean distances. Next, we observe the y outcomes of the k-neighbors. And finally, we classify the new data point as the most common category among the neighbors. That is, we take a majority vote. We've learned many algorithms, and all have their drawbacks. KNN is no different. First, KNN is what we call a lazy learner, and this is a technical term. In logistic regression, recall that we run the algorithm one time. This gives us a formula that we can then use to classify all future data points. But in KNN, we have to recalculate distances and identify neighbors, hence basically start the algorithm all over each time we want to classify a new data point. As a result, KNN can be computationally expensive to apply. Basically, we have to start over every time we want to apply it. Further, KNN provides classifications of y, but no real insights into the relationship of y with x, that is, how these predictions or classifications came about. With this in mind, we'll consider another non-parametric classification tool in part 2 of this video series.